Signal consists of a periodic component, a random component, and a DC component. The autocorrelation function is shown in the figure. So we have to decide the average power present in the random component. So in order to decide that one, first of all we have to subtract the DC power present in the autocorrelation function, which is not because of a random component. So DC power is equals to 1.5. So autocorrelation function due to the periodic autocorrelation function RP tau plus autocorrelation function due to the random component is equals to RYY of tau minus 1.5. So here this is RP of tau, that is periodic autocorrelation function is this is plus 0.5, this is minus 0.5, whereas autocorrelation function of a random component is this is 1 minus t, that is tau. So average power of a random component is nothing but Rx of 0, which is 1 watt, that is option D is correct. Signal m of t is given as 2 into sine of 1000 pi t, and the phase sensitivity constant is 5 radians per volt. Bandwidth of the PS signal is. Here, suppose if we are indicating PM signal with AC cos omega t. Here omega, that is, this is nothing but, suppose I am pi of t, this is the phase. So pi of t is equals to omega ct plus kp dm of t by dt. Kp m of t, this is because this phase, because m of t is in volts, the kp must be radians per volt in order to add to this constant to the radians. So here d pi of t by dt 1 by 2 pi is the instantaneous frequency, which is equals to fc plus kp by 2 pi dm of t by dt. So here delta f max, which is nothing but a maximum frequency deviation, is equals to kp by 2 pi dm of t by dt max. So kp by 2 pi d by dt, m of t is nothing but 2 into sine of 1000 pi t max. So after getting delta f max, if we substitute bandwidth in bandwidth, that is 2 into delta f max plus fm is equals to 11 kilohertz. That is option B is correct. Schematic is shown below. A white Gaussian noise whose mean is 0 as well as the whose power spectral density is two-sided one, that is n0 by 2. So if we look into that is PSD diagram of a white Gaussian noise is n0 by 2 for all frequencies. This is Sn of f. Here the filter transfer function is given in the question itself, that is this is located about the some center frequency and whose bandwidth is to be on both the sides, it is 1. This is h1 of f. This is a band pass filter. Comes to h2 of f, which is a low pass filter whose bandwidth is similar to that one, that is 2b, and the magnitude is 1 over the desired frequency range. Now Suppose I am assuming this is S1F, this is S2 of F. So S2 of F is equals to 1 by 2 S1 of F plus Fc plus S1 of F minus Fc. So if we plot this function, that is S2 of F, we will get this as N0 by 2. This is 2Fc minus 2Fc. This magnitude is N0 by 4. This magnitude is N0 by 4. So after passing S2 of F through a low pass filter, that is output Sn of F, that is nothing but this is 2b, that is minus b2 plus b, magnitude is N0 by 2. Here the time domain equation is, that is n of t is equals to minus b to b N0 by 2 minus j2 pi ft df, which is nothing but N0 by 2 e power minus j2 pi bt minus e power minus plus j2 pi bt divided by minus, this is plus, so j2 pi t. So if we solve this one, N0 by pi t to sine of 2 pi bt by, so this is 2 pi b, here b t, this is 1 by 4, okay, not 2, see 1 by 4, so we will get again these two, so N0 b divided by 2 sink of 2 pi bt, that is option B is correct. Total magnetic field intensity at 1.523 caused by a current filament of 24 amps in AZ direction extending from Z equals to 6 to infinite. Means suppose this is X, this is Y, this is Z. Current filament is located from Z equals to 6 to Z equals to infinite. So we have to find out magnetic field intensity at 1.523. So H is equals to 6 to infinite 6 of minus 2 ax cap plus 1.5 ay cap dz divided by pi of 1.5 square plus 3 minus z whole square 3 by 2. So if we solve this integral, we will get magnetic field intensity as 0.177 amps per meter. Hence option A is correct.